Following is the Unit 1 test review for chemistry. Question 1, is air considered matter? Yes, air is matter because it has mass and it takes up volume. For example, the air that you're breathing right now is mostly nitrogen, but it also has things like oxygen, carbon dioxide, and water vapor. Question 2, which of the following is the best answer for the correct measurement? Picture below. We have a ruler here that goes to the nearest centimeter. So you're going to be measuring to the next decimal place. This looks like it goes 1, 2, 3, 4, 5, and the measurement is between 4 and 5. Any decimal between 4 and 5 would be fine. Best answer they give is 4.7. Question 3, we've got a measurement for density of a substance. We're going to use D equals M over V. That's here. And our M is 232. Our volume is 25.8. That's milliliters. Our density ends up being about 8.99 grams per milliliter, which is really close to that one right there. Although I would check other physical properties to ensure that I was correct. Question 4 is measuring volume. Volume will be equal to mass divided by density. Our density for gold is given. That's 19.3. And the mass is given as 30 grams. That ends up being about 1.55 milliliters. Question 5. A graduated cylinder will measure liquid volume. It will measure liquid volume rather accurately compared to something like a beaker. Question 6. Describe what it means when something is labeled AQ. AQ stands for aqueous, which means dissolved in water. Lowercase l is liquid, which is something that is melted, something in an actual liquid state. Question 7. Symbols for potassium, mercury, lead, and tin. These ones are all kind of weird. Potassium is K. Mercury is Hg. Lead is Pb, bum bum. Tin is Sn. Describe the number of elements and atoms for Na2CO3. All right, Na is our sodium, and there are two of those. C is carbon. It's 1. O is oxygen. We have 3. Question 9. Name one element which will have similar properties to cesium. Cesium, Cs down here, in group 1. All of the elements in group 1 have one valence electron, like we've seen. They all will react in a similar fashion. For example, our alkali metals here react with water. Question 10. Identify one element which belongs to the following families. Alkali metals are these ones here. Noble gases are over here. Transition metals are these ones. Halogens are over here. Alkaline earth metals are here. These are all colored, etc. Identify as metals or non-metals. Everything over here is kind of where the periodic table is split. Everything on this side is a metal. Disregard hydrogen. Everything over here is a non-metal. Check chromium, oxygen, tin, lithium, neon against that trend. Question 12. Describe the most current model of the atom and draw a picture below. There is a picture here of a electron cloud diagram. This thing illustrates the probability their location. Doesn't tell you anything about the nucleus, though. When you heat up a sample of helium gas, you observe the following spectrum. It's what these multiple bands of light are called. What's happening inside an atom to cause this? Inside a helium atom, we've got the nucleus, we have 2 electrons. Around the outside of this thing, we have other shells that are unoccupied, but they are places where electrons can jump to. They'll jump because they're excited, fall because they can't stay, it's not a stable configuration. When they fall, they emit a photon. That photon of light can be a different color depending on how far they fell. They fell further, they have more energy, and have a shorter wavelength. They actually have more energy in this direction. Question 14. We need the total number of electrons, number of valence electrons, and number of core electrons so far. For silicon, arsenic, and selenium, the total number of electrons is the atomic number. Silicon would be 14, arsenic would be 33, selenium would be 34. The number of valence electrons is related to the group number. While these are in groups 14, 15, and 16, we also have them listed as 4A, 5A, 6A, because that is the number that represents the number of valence electrons. Silicon would be 4, arsenic would be 5, selenium would be 6. For our core electrons, you're just going to subtract the two of these numbers. Subtract, 10, 28, and 28 again. All right, looking at mercury. Symbol of the element is Hg. It's based on its Latin name. Name of the element is mercury. This one has 80 protons. If I subtract the mass and the atomic number to find the number of neutrons, it will most likely have 121 neutrons. If it was neutral, it has the same number of protons as electrons. This is a weird question. Mercury is a transition metal, and they all have 2. Sorry if there was some loud noise there. Apparently, Ted turned up the volume on the TV. Anyway, all of our transition metals have 2 valence electrons. As far as core electrons go, take your total number of 80 minus 2, which is 78 core electrons. Another element with similar chemical properties would be anything in the same group as mercury. It could be zinc, cadmium. Is this a metal or non-metal? It's a metal. It's on the middle left side, definitely on the left of the metalloid staircase. So it's a metal. Question 16, the atom of magnesium has 14 neutrons. Would have what mass? Now, the mass given here is the average of all of the isotopes of magnesium. For this magnesium, it has 12 protons, 14 neutrons. Add them together, we end up with 26 for the mass. The symbol for this then would be Mg with the 26 on top and the 12 on the bottom. We're an isotope for an atom with 11 protons and 12 neutrons. The mass of that would be added together 23 over 11, and that is in fact sodium. Uranium has 3 common isotopes with a bunch of different abundances, a bunch of different masses. We have a lot of work to do this one. We're going to come up with the average atomic mass. Should be something close to what's listed on a periodic table. For each isotope, we need to multiply the abundance times the mass. So for U-234, the mass is 334. And even though it's 0.01%, we actually need a decimal for that. It'll be 0.00001. 0.01%. We're going to add that to 5 times its abundance, which is 0.0071, and 238, which has an abundance of 0.9928. Clearly, from this, we figured a number very, very close to 238. Let's do some math. This ends up being 0.234. This ends up being 1.6685. And this ends up being 236.29. Together, this ends up being a total of 238.19, which is pretty darn close to that. List the following in order of increasing atomic radius or size. The trend for radius is bigger this way and this way. This question is a little bit tricky because we are looking at elements and comparing them that are not in the same row or column. I think we could safely say that fluorine is the smallest, then likely chlorine, sulfur, and bromine. Although we could have an argument about which of those two is bigger. Question 20. What happens to the mass number and atomic number in alpha or beta decay? So alpha decay, there's our little alpha symbol. The mass number, you lose 4. An atomic number, you lose 2. In beta decay, and there's our beta symbol, the mass does not change. The atomic number actually goes up by 1. Write the equation for the beta decay of gold 201. Gold 201 has atomic number of 79. Because this is decay, right, we're going to end up with a different particle. It's going to be a beta particle, which looks like an electron. Mass-wise, does not change. We still have 201. And like we saw before, the mass number will increase by 1. You'll end up with 80. What element has a mass 80? Mercury, 201. So that'd be an atomic number of 80. Write the equation for the alpha decay of platinum 192. 192 is our mass. Platinum has an atomic number of 78. An alpha particle looks like, oh boy. Apparently Ted doesn't like my narrating style. An alpha particle looks a lot like a helium nucleus. In this case, we would lose a mass of 4. We would lose atomic number of 2. And an element with an atomic number of 76 would be osmium. Write the equation for the fusion. Fusion means we're going to smush 2 elements together. We've got helium-4 and neon-20. Helium-4 looks like this. And just because there's a helium atom in this nuclear equation does not mean it's alpha decay. This is a fusion reaction. We're going to add to it neon-20. Now all we need to do is add them up. This arrow is like an equal sign. 4 and 12, which makes it magnesium. The difference between a chemical and nuclear reaction. Chemical. This will not change elements in a nuclear. It will change elements. Question 25. Nuclear fission and fusion. Compare and contrast. We can do a Venn diagram. All right. What's the same about them, right? What we're comparing here. is that these happen in the nucleus. For fission, we split. Even Ted knows that. In fusion, the elements are smushed together. Or fused. Thallium-208 has a half-life of 3 minutes. How long will it take for 120 grams to decay to 7.5 grams? Every half-life will split our remaining amount in half. So we'll go, let's say, half-life versus grams. At 0 half-lives, we have 120 grams. At 1, split it in half, we have 60. At 2, we have 30. 3, we have 15. And at 4, we have 7.5 grams. Each half-life is 3 minutes, so 3 times 4 is 12 minutes. Question 1, investigation 5. A chunk of potassium has a mass of 700 grams. How many moles of potassium is it? Here's our mass for 1 mole of potassium, right? 39 grams per mole. I'm going to set this up with dimensional analysis. Just have 700 grams of potassium. Yeah, he hates it more than you do. 700 grams of potassium. We're going to set this up with grams on the bottom and moles on top so that grams will cancel. Turns out that's our 39 grams. Potassium is 1 mole. We can cancel. And 700 divided by 39 is about 17.9, in this case, moles of potassium. Iodine crystals in copper metal contain the same number of moles. If the copper has a mass of 127 grams, what's the mass of the iodine sample? Two-step problem here. We're going to go from grams of copper, 2 moles of copper, using dimensional analysis. 1 mole of copper is 63.5 grams, which is equal to 2 moles of copper. We have the same number of moles of copper as we do iodine. So we also have 2 moles of iodine. We want to convert that into grams of iodine, right? Mass of iodine. We're going to do that by multiplying by the the molar mass of iodine, which is 126.9 grams of iodine per mole. That is equal to about 253.8 grams of iodine. How many grams would 3.5 moles of nickel weigh? We're going to again multiply by a fraction equivalent to 1. For nickel, it is 58.7 grams per mole of nickel. In this case, our moles of nickel will cancel. This is equal to 205.5 grams of nickel. Hope you're enjoying the commentary. Would you contain more atoms, 10 grams of copper or 10 grams of carbon? We would have to compare the moles. We really don't even need to do any math for this one. Because carbon has a lower molar mass, it will have more atoms per the 10 grams. Identify the element. We have 15 moles of it. It has a mass of 104.2 grams. If we want to find the molar mass, which is what we're going to use to identify the element, we need something grams per mole. We have here 104.12 grams per our 15 moles. That's equal to about 6.9 grams per mole. which makes this lithium. We want to mass out 0.1 moles of FeSO4 to make a solution that will burn in a flame test. How many grams of... In order to calculate moles, first we need to get the molar mass of the whole darn thing, FeSO4. We have one copper atom here, which is 53.5 grams per mole. We have 4 oxygen, so that's 4 times, we'll call it 16 grams per mole. And sulfur we have 1, which is 32 grams per mole. This will all need to be added up to get about 159.5. Now we are starting with 0.1 moles, which we're going to multiply by our 159.5 grams per mole. Cancel, cancel. We end up with 15.95 grams of CuSO4. The student dumped 123 grams of HCl into some water. The molar mass of HCl would be 36.45 or so grams per mole. We'll start with 123 grams of it. We'll multiply by a fraction of 1 mole over our 36.45 grams, which is equal to about 3.4 moles. Question 8. What is the molar mass of TNT7H5 at 306? Got a lot of work to do for this one. For hydrogen, we have 5 of them. And they are about 1 gram per mole each. For carbon, we have 7 of them. And they are 12 grams each. Oxygen, we have 6 of them. They are 16 grams each. Nitrogen, we have 3. And they are 14 grams each. Equal to 5 grams of hydrogen, 84 grams of carbon, 96 grams of oxygen, and 42 grams of nitrogen. This is all equal to about 227 grams per mole of TNT.